the whole idea of a fit is strange. But I'm not going to think that. Model works best when we got a sample size that includes lots of zeros and ones, as opposed to just all zeros or just all ones, or just a few zeros and just a few ones. We'd like to have both the purchases and the non-purchases at least well represented. Religion's model will get to it. All right. The likelihood ratio test, essentially this is like doing an F test. Let's kind of skip through that. So, yeah, essentially what we're doing is, again, like an F test, you run a restricted model, you run an unrestricted model, and then you compare the likelihood statistics. And the likelihood statistics are is that thing. So that's our likelihood statistic for this model. That was our F statistic, F test. All right. For the likelihood ratio statistic, instead of that big ugly formula, we basically take the likelihood ratio statistic from the unrestricted model, LU, subtract it from the likelihood ratio statistic of the restricted model, LR, and multiply it times 2. It's a pretty simple test. So, let's see. Let's go to this. Here's our unrestricted model. We got price in there. We get a likelihood ratio statistic of 822, negative 822. Here's our restricted model where let's just exclude price. We get a log likelihood ratio statistic of negative 6, 7. So we take those two, subtract one from the other, boom, minus that, multiply it times 2, and we get that 291, which is essentially our likelihood ratio chi-squared statistic that is contained there. So we can do this this is a relatively simple model with only one independent variable, but if we had multiple independent variables, we can test any subset of variables. So we can exclude, we don't necessarily have to exclude all of them, we can exclude one or two of them and see if it changes the model much. The fewer the independent variables, the better, usually. We can look at the chi-squared statistic, which would be 3.84. 291 is clearly greater than 3.841, but really all we have to do is look at the p-value, the probability that greater than chi-squared, and that's 0, so that would tell us the same thing. 0 is good. 0 means we're going to reject the null hypothesis, reject that our independent variables are equal to 0, assume that our model has some explanatory power. And that is perfectly analogous to what we did with the F test. Reject the null hypothesis. All right. McFadden's R squared is, it's kind of burned. But essentially McFadden's R squared, pseudo R squared, is the ratio of our restricted model, unrestricted model, divided by our restricted model, subtracted from 1. You see the Nobel Prize for that. And that equals 0.15, which is what we see up here under our pseudo R squared. So pseudo R squared, again, the higher the better, but you're not going to get R squareds that are going to be too high. I can't imagine. Or at least I haven't come across it. Again, it doesn't have the same interpretation as our ordinary least squares regression R squared because it's not really a measure of fit. Not sure what measures. All right, what else do we have in here? This is the tricky part. It would be nice if we could say, right, coefficient on price is negative 0.75. It's negative, meaning the law of demand holds, which is good. It would be nice to say for every $1 increase in price, the probability of purchasing goes down by 0.75. That's how we interpret the linear probability model. It would be nice to say that, to interpret it that way, but you can't. The interpretation of these is awkward at best. So, essentially if we were to kind of plug in for some price, where we know that into some transformation, and the functional form of our transformation is the cumulative standard normal distribution, essentially what we get is, let's try it. So we plug in for, let's say we evaluate this at $5. Constant minus the coefficient on price times some price times some price, we get this number of 0.34. Again, it would be nice to think that that's the answer, that's the probability of purchasing at a price of $5. But it's not. It's actually the z-statistic associated with the standard normal distribution of purchasing at a price of $5. That's strange. So again, plug in a value for price, we get a number. This number is not the probability of purchasing, it's the z-statistic associated with the probability of purchasing at $5. And that's why these are awkward interpretations. So if we go back to our standard normal distribution, a z-statistic, remember it's centered on 0, so a z-statistic of 0.34 is going to be just over 0, which means the probability of purchasing is going to be what? Greater than what?
Greater than not purchasing.
Greater than 50%. 50%, exactly. So we know half the distribution is going to be 50%, so we know the probability of purchase. So any z-score greater than 0, the probability of purchasing is going to be greater than 50%. So if we took the transformation, so if we take that 0.34, put it into our formula, take the integral, we would find the area to the left of 0.34, and that would be the probability of purchase. So the probability of purchase would be 0.63. So we know it's going to be above 0.5.
This is why people don't use probability.
They're hard to interpret. But state is going to make it easier. So at a price of $5, the probability of purchase is going to be 0.63. So it fits into the model. It's into our axis. All right, so these are our predictions. The marginal effects, which are basically the coefficients, basically we want to look at two things, the sign and the significance. If it's positive, then it's going to increase the probability of purchasing. If it's negative, it's going to decrease the probability of purchasing. So the coefficient on price is negative, so it's going to decrease the probability of purchasing. The law of demand is going to hold. Increases in price reduce the probability of purchasing. Decreases in price increase the probability of purchasing. Beyond that, the coefficients are not interpreted very friendly-wise. In essence, the coefficient represents the change in the z-statistic associated with the change, with the 1 unit change in x. So, as price increases by $1, the z-statistic associated with the probability of purchasing decreases by 0.75. I don't know. Again, it doesn't really tell us much. we need to be able to convert these to actual probabilities. But the outputs from the probit model are, again, difficult to interpret. They do have an interpretation, but it's a difficult interpretation. But again, what we want to look at is sign and significance. It's negative log man-holds, it's significant. It is Z statistic, it's significant. So we're good, we're fine. It's nonlinear. Remember, the effective price is constant on a straight line. The slope is constant. So not only are these the Z statistic, the change in the Z statistic associated with probability of purchasing, that's the slope, or those marginal effects, are going to change throughout the range of our prices. So again, as we can see, at prices above, what would you say, $7 or $8, the slope's close to 0. So the effective price change is going to be relatively small. At prices at the other extreme, again, these are people that have already made up their mind to either not buy on this flat period, on this flat portion, or buy, which would be on that upper flat portion. The slope is close to 0, so that price has very little effect. The marginal, where the slope has the biggest effect, where price will have its biggest effect on determining whether or not we purchase, is going to be at that probability of 0.5, where we have the marginal consumer. You're sitting on the fence. Outside of that, we're going to have to figure out a way to make this stuff a lot more intuitive. And the way we're going to do it is really by using these visuals. If we can map this out, it looks a lot like demand curves. So if we can understand demand curves, we can understand these, what we'll call binary demand curves or nonlinear demand curves, where it's not a quantity purchased, but the probability of purchase. Any questions? Because this is not very intuitive stuff.
So that equation that you plug the Z statistic into, we're going to have a stated magic way to do that?
Exactly.
Okay.
So, if we wanted to know the probability of purchasing at $5, we plug it into that formula, and that gives us the Z statistic associated with that probability. So remember, and what was the Z? That was the 0.34. So remember in stats, when you took stats, you probably had the Z tables at the back of the book, and you looked up the Z statistic and it gave you a probability. Stata is going to do that for us. So we're going to get the Z statistic, Stata is going to convert that to a probability. And we're going to, we'll be happy. So, yeah, we don't want to do any of this stuff, but we don't want to take that integral. In all honesty, I don't think I could take that integral right now. I haven't had to take that integral since grad school, and I didn't enjoy it then. But I passed, so I'm not going to make you go through that. All right, interpreting the marginal coefficients. Again, these are changes in probabilities. These are just more math stuff. But we can see that the effect of a $1 change is going to be different at different prices. So the effect of a $1 change at a price of $2, imagine where $2 is there. At a price of $1, I'm sorry, $1. No. At a price of $1, the effect of a $1 change on the probability of purchase would be that, which would be there. So there's a price of $1. The probability of purchasing is really high. It's about, you're pretty much going to buy. At a price of $1, you're pretty certain to buy. You're almost certain to buy. Not 100%, but you're almost certain to buy. You're real close to 100%. So are small changes in price going to affect your decision? No. And you can see that. The slope is 0. The slope is close to 0. Well, we know what the slope is exactly. The exact slope is 0.009. So yeah, a higher price is going to reduce that probability, but you're still going to be it's still gonna be a pretty high probability of purchase. The same thing. A lower price is gonna increase that probability, but it's not gonna increase it by much. So that slope is close to zero. The effective price, small changes in the effective price are not gonna have much of an effect. So it's a good deal. You know it's a good deal. You know, even if they increase price, it's still a good deal. All right, so let's look at a price of $6. And we can see that over here. And now we're in a portion where the slope is steep. So again, the effect is going to be 0.27. So let's see, where are we? At a price of $6, yeah, a $1 increase in price is going to actually reduce the probability of purchasing by quite a bit. We'll reduce it by 27.73 percentage points. If we were to increase price by $1, there would be a fairly significant change. Oops. Marginal effects, much more influential in that middle portion where the slopes are steep versus the extremes where the slopes are literally flat and close to zero. And by the way, you can see, so I can't do it on this one very well. But you can see how some people may want to use a linear probability model because that middle part is almost linear. So it's almost a straight line. We know it's not linear, but it could probably be approximated pretty closely to a straight line, assuming that's where the linear probability model fits. But we know it can fit kind of awkwardly in different places. So that's one of the excuses why someone might use a linear probability model. Well, it's pretty close to the Probit model or Logit model. All right, the other model we're going to use is called the Logit model, and it's really doing the same thing. It's based on a different distribution, which just so happens to be normal looking, shaped, kind of like the standard normal distribution. And it has a similar cumulative logistic distribution, a lot like the cumulative standard normal distribution. So these are very, very similar regressions. It's also going to be bounded. It's also going to be bounded. The difference between the Logit, or the logistic distribution, and the normal distribution is that the logistic distribution has heavier tails. So in the extremes, you might see some difference. Although one of the things we're going to do in the problem set is kind of compare these two and compare the predictions, and you're going to find out they're not very different. They're usually going to be pretty close. All right, so the model is estimated as, again, just strange, weird wackiness. It's estimated as the log of the probability of purchase over 1 minus the log of the probability of purchasing. And this is called the odds ratio. And again, just to remind ourselves that odds and probabilities are a little bit different. If something has a probability of 25%, then the odds are going to be 1/3. If you can. And this is going to be important. Kind of understanding this is going to be important in actually using the Logit model on how the probabilities are converted from the log of the odds ratio into a probability. So we're going to have to use that. Again, the coefficient estimates are going to tell us, the marginal effects are going to tell us the change in the log of the odds ratio for when you change in independent variable. Let's get an output. There's an output. There's a Logit output. Again, it's the change, the coefficients represent the change in the log of the odds ratio. Again, it doesn't have any interpretation. Basically, you want to look at the sign and significance. If it's negative, which it is, then it decreases the probability. If it's positive, then it increases the probability. So look at the sign, look and see if it's significant. I don't honest, it's just difficult to interpret. We know we have a measure of fit called the pseudo R-squared. In the field, in jobs where you're going to be actually doing this stuff, pseudo R-squared isn't used that often. It's really more of an academic calculation. What's used instead is something called the hit rate. And the hit rate is much more intuitively a measure of how well the model predicts the data. Not fits the data, but predicts the data. And I think that's a better interpretation. So what we do is this. We run our logit or our probit, and we get the predicted values. So we do like we did in ordinary least squares. We run our logit and probit. We use predict. The predict command, it's going to predict us instead of predict our nice. I should probably reverse this, because that's how we run the regression. Quantity, price. Here's our data. Here's our estimated demand curve using ordinary least squares regression. So when we use the command predict, it takes the regression and it finds the line that best fits. So these are all our fitted predictions. The same thing with the same thing happens with logits and probits, except instead of predicting values, it predicts probabilities. It says that for any given price, for example, it's going to predict the probability of purchasing. And these are our predicted probabilities. Okay. So what we're going to do is take our predicted probabilities and convert them. Remember, our predicted probabilities are going to be between 0 and 1. We're going to take our predicted probabilities and convert them back to zeros and ones. So if your predicted to purchase is greater than 0.5, we're going to convert that back to a 1. If your predicted value to purchase is less than 0.5, we're going to convert that back to a 0. So logit and probit creates these probabilities of purchasing. We're going to take those probabilities of purchasing and convert them back to zeros and ones. And then in essence, we're going to take our predicted zeros and ones and compare them with our actual zeros and ones. So how do we do that? We look at something called the percentage of predicted correctly. The first one is going to be, remember the tildes are our reconverted zeros and ones from our predicted probabilities. The y's are our actual zeros and ones. So we're going to take the number of people we predicted to buy, number of ones we predicted, and compare that to the actual number of ones that are in the data. And we want to see the percentage of ones that we predicted correctly. So how many of these ones, these actual ones, so how many people in the data that actually purchased were correctly predicted to purchase? Does that make sense? So how many people in the data that actually purchased were correctly predicted to purchase? And that's our percentage of ones predicted correctly. And that would be in this table. We're going to have actual or observed, and then our zeros and ones, and then our predicted zeros and ones. So this is 1, this is the number, the percentage of people that actually purchased that were predicted to purchase. This is referred to as sensitivity. All right, then we're going to look at the zeros. We're going to look at the people that didn't purchase, and we're going to compare that to the number of people that were predicted to not purchase. And that's that horizontal column in our table. I'm sorry, that horizontal spot in our table. 0 zeros. This is the percentage of zeros predicted correctly. This is referred to as specificity. And there's a trade-off between these two things. The more sensitive we get, the less specific we'll get. The more specific we'll get, the less sensitive we'll get. And it's interesting where these terms came from. It actually came from the military. And in the Navy, where you're on the battleship, it was during World War II, and you had people looking out for German airplanes that might bomb the boats, the ships. So you got someone out there with their binoculars, and they're looking for, clusters of German airplanes. And essentially, what you want to do is be able to identify the German airplanes. You don't want to identify a cluster of seagulls and then sound the alarm and have everyone going nuts trying to get ready to fight off the Germans. And that's the sensitivity. You don't want a test so sensitive that it picks up every little flying object. You have to reduce that sensitivity, you're going to get less specific results. So sometimes you're going to have false positives, sometimes you're going to have false negatives. So that's where the terms come from. The weighted average of these two things is going to be called the hit rate. But you also might want to look at the other ones. And very often you're asked to show these. So these are your incorrect predictions. So this is people that didn't buy, that were incorrectly predicted to buy. So they didn't buy, but they were predicted to be ones. So these are false positives. We're predicting that this person buys if they don't buy. This is the opposite. These are ones, so people that actually bought, but they were predicted to not buy. And these are false negatives. So usually we like to construct a table like this so that we can answer questions on, basically answer any of these questions. How many people that bought were correctly predicted to buy? So these are a lot better than the pseudo R-squared, which gives us, again, some number. Higher numbers better than a lower number. These answer more specific questions in terms of our predictions, as opposed to pseudo R-squared. And again, there's 20 at least pseudo R-squareds out there. A research assistant of mine invented his own too. I don't know where he came up with it. I think it was Heavy 92. They got a new R-squared, pseudo R-squared. Normally you want your hit rate above 0.5. Remember 0.5 would be flipping a coin. Is this person going to buy? Sure. He's got a 50% chance of buying. So normally you want your hit rate above 0.5. The higher above 0.5, the better. So useful table. Some graphical measures of fit. One is called the Lowe's regression. And Lowe's regressions are pretty cool. Essentially what you're comparing is, the probability of purchasing Heinz, predicted probability of purchasing Heinz, against the fraction of actual purchases. And you have a 45-degree line, and the closer you are to that 45-degree line, the better the fit. the better the predictions. So the solid line is this Lowe's regression, and essentially what a Lowe's regression is that it runs it literally runs a bunch of local regressions. So it runs regressions on this data set, and it's like a moving regressions. It runs a bunch of moving regressions, kind of like a moving average, but it runs regressions on these moving samples. So it can be kind of computationally intensive. And again, we want to be able to get as close to the 45-degree line as possible. This is the data we're going to use. But it shows that the probability of the predicted probabilities are more accurate the higher the probability of purchasing lines. We'll see why that could be true. Another measure is called a receiver operating characteristic curve. And this is kind of the opposite of the Lowe's regression. For the Lowe's regression, we wanted that line as close to the 45-degree line. For this one, we're again trading off or examining the trade-off between sensitivity and specificity, or 1 minus specificity. And what we want, with the percentage of ones predicted correctly, which we call this sensitivity, against 1 minus specificity, which is the false positives. And we would like to see a couple of things. One, it shows the trade-off. And we'd like the receiver operating curve to hug against the left axis and up against the top axis. So we want it as far away from that 45-degree line as possible. So we want it hugging those outer places. And essentially the area under that 45-degree line is kind of like a measure of the accuracy. And it's given to you in the curve, but the 0.79 is, again, it's going to be between 0 and 1. The 0.79 tells us that, again, higher is better, and it tells us that we have a pretty decent prediction. The model predicts pretty decently. Ignore the slope of the tangent line, gives us the likelihood ratio for the test. Yeah, we're probably not going to use that much. Basically, we look at it and see, okay, are we hugging that left border and that top border? Yeah, and again, the area under the curve of 0.79 is not